Do you know when this experiment first time conducted? This experiment was conducted by Galileo Galilei in 1602. So first time this experiment was conducted by Galileo Galilei in 1602, and it is historical experiment. Yes, I am going to talk about simple pendulum today, and this is there in your syllabus for 11th and 12th standards in many universities of India. So I am going to cover the common topics from all universities. So stay with me till the end of this video. Many of my students, they ask a question, sir, why to study simple pendulum? What is the importance of this experiment? So first let me answer this question, why to study simple pendulum? After that, I shall be providing you more technical information about simple pendulum. So simple pendulum help us to understand the complicated waves, sound waves, light waves, seismic waves, any other kind of wave. We can easily understand them and we can easily demonstrate their physical, practical way to express these waves, to understand these waves. We use simple pendulum. Another application of simple pendulum is to find acceleration due to gravity. By using this formula, that is T equals to 2 pi under root of L upon G, where L is called as the length of simple pendulum. By using this expression, we can find acceleration due to gravity, that is G equals to 4 pi square multiplied by L divided by T square. Let us talk about the third application of simple pendulum, that is to study the conservation of energy. We know that whenever we talk about a system, there are the two energies associated. One is the kinetic energy, another is the potential energy. If you add both the energies together, you will get a constant. It's fixed value. Kinetic energy plus potential energy equals to fixed value. This fixed value is called as a constant. When the potential energy reaches its peak value, kinetic energy becomes zero, and when kinetic energy becomes maximum, potential energy becomes zero. So one kind of energy increases, another kind of energy decreases, but the addition of kinetic energy and potential energy remains constant. So this equation, the addition of kinetic energy and potential energy equals to constant, that is nothing but conservation of energy. This conservation of energy can be easily demonstrated, easily proved by using this simple pendulum. Intensity of earthquakes can be measured by using seismometers. You see, seismometer, we use a pendulum, heavy pendulum. This heavy pendulum cannot move. What is the reason? Because of inertia. But the frame shakes. So the bob of the pendulum is attached with the pencil arrangement as shown in this picture. So as the frame is shaking, but the pendulum is remaining same due to the inertia, the pattern of the earthquake can be easily drawn. So this is another very important and very practical use of simple pendulum. Now let us discuss about technical information about simple pendulum. First of all, let us talk about length of the simple pendulum. Why to find length of the simple pendulum? The reason is period of oscillation depends upon length of the simple pendulum, as well as the frequency of oscillation also depends upon length of simple pendulum. The period is denoted by capital T and frequency is denoted by small n. So this is the reason we need to find length of the simple pendulum. Now what exactly the length of simple pendulum? Length of the simple pendulum is nothing but the distance between the point of suspension and the center of gravity of the bob. So distance between these 2 points is nothing but called as the length of simple pendulum. Now next important parameter about the simple pendulum is angular displacement. What is angular displacement? It is a vertical angle the thread of the simple pendulum makes with the vertical. So theta is the angular displacement here. It is the distance made by the string with respect to resting position of the simple pendulum. Point O is the resting position. So thread of the simple pendulum making angle theta at a given instant of time. It keep on changing. The pendulum oscillates between two extreme positions A and B. M is the central position. It is called as the mean position. If the pendulum is displaced through the small angle theta and released, then this pendulum automatically oscillates both the side, left side as well as the right side, keep on oscillating, and these oscillations are observed with respect to mean position. And if this theta is small means near about 10 degrees. If theta is small, then the bob of the simple pendulum performs simple harmonic motion. So we can state, for small angular displacement, bob of the simple pendulum perform simple harmonic motion for the small angular displacements. Theta should be small enough. It is near about less than 10 degrees. Up to 10 degrees it is allowed. Generally in college lab we just displace the pendulum to the 10 degrees. What is simple harmonic motion? Simple harmonic motion is one when you are displacing the bob away from the mean position, then it is always come back to the mean position with certain acceleration. So the acceleration of the bob is opposite to the displacement, and its magnitude depends upon angular displacement. More the angular displacement, more the acceleration. So we can say the bob of the simple pendulum performs simple harmonic motion only if theta is small, and if the pendulum is under oscillating condition, moving left to right, right to left, that is swinging left to right. In that case, we need to talk about two forces. What are these two forces? One is the tension and another is the weight of the bob. So tension, this is denoted by T dash here. So this tension is acting in the upward direction, and tension is acting towards the support point. O is the point of support. So tension is acting in the upward direction and always toward the point of suspension, and the weight of the bob acting vertically in the downward direction. So whenever the pendulum is moving left to right, right to left, then the two forces, one is the tension in the string and another is the weight of the bob. Now this weight of the bob, that is mg, can be resolved into two components. First one mg cos theta and the second one mg sin theta. So mg can be resolved into two components, mg cos theta and mg sin theta. This mg sin theta is a kind of force. What is the effect of this force? The effect of this force is trying to take the bob from extreme position towards the mean position, like this. So mg sin theta equals to restoring force. It is called as a restoring force. Now the another force, that is mg cos theta. Mg cos theta exactly opposite to the torque T dash. They are equal and opposite. So mg cos theta is balanced by tension in the string. Since we are considering smaller angular displacement, so if theta is small, then we can say sin theta approximately equal to theta, and theta is given from this diagram x upon L. So we have theta equals to x upon L, call it equation 1. Then restoring force equals to minus mg sin theta, because restoring force is directed opposite to the displacement. Putting the theta value, so we get F equals to minus mg x upon L. Call it equation number 3. Since m, g and L are constant, mass, gravitational acceleration and length of the pendulum are constant. Therefore, F is proportional to negative x. From this expression, it is clear that for the smaller displacement, the restoring force is directly proportional to the displacement and oppositely directed. Thus, the bob of simple pendulum performs simple harmonic motion for smaller displacement. Why simple harmonic motion? Because the restoring force acting on the bob is opposite to the displacement from the mean position, and this restoring force is always directed towards the mean position. So two conditions of simple harmonic motion are valid here. Therefore, we can say simple pendulum, that is the bob of the simple pendulum, perform simple harmonic motion. Now the next topic I am going to talk about, that is to find expression for period of simple pendulum. We already know that the period of simple pendulum t equals to 2 pi multiplied by under root of L upon G. But how this expression has come? From where this expression has come? What is the concept of this expression? That is what I am now going to talk to you, and I am going to obtain this expression. It's very simple. So once again, this is x, we already told you, and the linear acceleration of the bob, let us say a equals to linear acceleration of bob. Now we also know that F equals to ma, mass into acceleration. F is also restoring force in terms of linear acceleration, and the F equals to minus mg x upon L is also restoring force in terms of gravitational acceleration and length of the simple pendulum. Both equations are one and the same. Therefore, we are comparing them. So m into a equals to minus mg x divided by L. Now dividing both sides by m, so m and m get cancelled. We get a equals to minus g x divided by L. Now dividing both sides by x, so x and x get cancelled. We get here a upon x equals to minus g divided by L. So what is a upon x? A upon x nothing but acceleration per unit displacement. Now considering only magnitude, so magnitude of a upon x equals to magnitude of minus g upon L. So in magnitude, a upon x equals to g divided by L. Now the question is, why we got a upon x value, acceleration per unit displacement. So we got this value to find out the period of simple pendulum. The period of simple pendulum is given by t equals to 2 pi divided by acceleration per unit displacement. A upon x nothing but acceleration per unit displacement. Therefore, t equals to 2 pi divided by under root of g upon L. This can be written as 2 pi multiplied by under root of L upon g. So this gives expression for period of simple pendulum. And now if you wish to find frequency of simple pendulum, then how to find that? That can be also obtained very easily. The reason is the frequency is reciprocal of period, so t equals to 1 upon t, so that is equals to 1 upon 2 pi multiplied by under root of g upon L. So this gives the frequency of oscillation of simple pendulum. It gives the frequency of oscillation of simple pendulum.